everyone for being here and coming for this really exciting talk with Andy, who also makes the phenomenal earrings, by the way, like, big shout out. Talk about quantum computing, which is one of the most interesting and exciting, I think, topics in technology and science today. It is a completely new way of approaching computation and computing based on quantum mechanics, which is such an interesting part of science and a topic that I just really highly recommend everyone to take a look into. I promise it's accessible, even if it might be complicated to understand. It's definitely interesting to learn about, so Andy will make sure that we all take something away, remember, and focus on later. And I'm a proud member of Represent AI, so thank you so much, Sarah, for starting the community. Like she said, now more recently, probably. It's very important to have these communities, to stand together, to have these events together. So this is really exciting for us. And then I'm also obviously a proud member of the IBM Quantum Ambassador community, which is led by Andy, which we will talk about a bit more soon. And I'm also obviously an IBM employee, so we do really exciting things at IBM in quantum computation. So Andy will talk about that a bit more in this talk. So, Kush, do you want to introduce yourself?
Yeah, I'm Kush. I'm also an IBM employee. I don't quite work in the quantum space, but I'm a software engineer, and I think everyone in this room is interested in quantum or has some sort of excitement about the space. It's the next big thing, at least from my perspective, and I'm excited to not just hear more from Andy and what he's going to share, but also all the exciting development within IBM and around the world. And yeah, I'm also part of the Represent AI group. That's the other part of the area I'm interested in, AI and the technology behind it, which is quite fascinating. And I'm looking forward to hearing from Andy.
Brilliant. Thank you. Is that me then?
Yes,
Right, over
take
to me
it
then. Right.
Take it away.
Where are you going to sit?
I'm going to
Sit
sit
over
there.
Right. People moving around. Just sort of these little windowy things that have all popped up on my screen. There we are. Okay. Right. So my name's Andy Stanford-Clark. I'm one of IBM's distinguished engineers, which means I'm one of our very senior technical people at IBM. I've been at IBM for 34 years, long before quantum computing was a thing, I hasten to add. I actually work in IBM research as an innovation leader. I won't talk too much about that. I'm also a master inventor, which in IBM means you've got lots of patents. Marie asked me earlier how many I got, and I said 44. Then I thought, oh no, I got another one last week, so it's 45. When I got 42, I tried to stop because I was like, oh, big Douglas Adams-y sort of number. So 42, how apt. But then I accidentally got included on another patent. 43, so then I had to carry on. Not sure what the next cool number is. It's 50. Anyway, for the purposes of this talk, I lead the IBM Quantum Ambassador team. IBM tries to quite carefully control the external story about quantum computing, so it doesn't accidentally get overhyped by overexcitable vice presidents and senior people. You know what I'm talking about. And the media is doing a perfectly good job of overhyping quantum as it is without us fueling that fire. Marie is one of my recent joiners of the ambassador team. We've got about 20 people who are highly trained by IBM to go out and tell the quantum story to anybody who'll listen. So we speak at conferences, media engagements, clients, so quite often going to see clients. And it's just a fascinating story. It's all in addition to our day jobs, so whatever everyone's doing, in cloud or writing software or whatever it is, the quantum ambassador's doing this because I think quantum's just such a cool area to be in. And that's all right. I'm sure it'll start. It's all right. I'm highly trained in this. Yes, it does. Right, there we go. We'll move the mouse over to the side. It won't bug us. There we go. Mouse on the screen. Right. So we are at the moment with quantum computing, where we were with classical computing, by which I mean the computers that we have today. So I'll refer to classical computers quite often. About 50 years ago, it was a big room full of clanking machinery with people in white coats tending over it. And if you'd have walked into that room then and said, oh, 50 years' time, all that and more will be in your pocket. And by the way, you'll buy another one when the manufacturer thinks you should every 18 months. Laughed at you and chucked you out the room. So if I say one day quantum computers are in your pocket, it seems ludicrous to me at the moment, because they're big machines, as we'll see later, but one day there might be a QPU, quantum processing unit chip, on the circuit board of your computer next to the GPU, the graphical processing unit, next to the FPU, the floating point unit, and it'll just handle the quantum part of the computation naturally, and the libraries will automatically call it. So I mean, that's all in the future. It's not imminent, they're quite big, but never say never. In 50 years' time, we'll look back and go, remember when quantum computers only had 127 bits, qubits? Same as people like John, sorry, not to pick on you. Probably remember when your ZX Spectrum only had 1 kilobyte of RAM, or less. You're probably going to have some even less. 256 bytes of core. So, I mean, we are at such an early stage in the science, which is why it's so exciting. Why people like me and Marie and others have got into quantum, because like once in a lifetime, it's the start of a completely new paradigm for computation, which, all hyperbole aside, that's pretty exciting. So, quantum computers can solve, they're not general purpose computers, they're not Turing complete, so they can't do everything. For example, they can't do things like if, then, else, or for loops, but they can do certain computations very well, which classical computers can't. And the main thing they can do well is searching very large search spaces, exponentially large ones. So there's quite a lot of problems over here, which are very difficult to do on classical computers. Now, at the moment, we either don't do them, or we approximate the answers. One good example is the travelling salesperson problem, where you've got to visit the GPD delivery driver, you've got to visit all the houses, minimising the amount of diesel they use. So they load up in the morning. Finding the optimal solution to that is what's called NP complete, so it's exponential in the number of towns or number of houses you have to visit. And it rapidly gets ridiculously out of hand. So if you've got 100 houses, you're talking about millions of years to compute the optimal solution. So we don't, we just come up with an approximation about 90% accurate, which we can do quite quickly, and that's good enough for the average DPD driver. But there are some problems which we call intractable, that computationally can't be done. And as a classically trained computer software engineer for many, many years, there are certain problems when I look at them and go, oh, not even going to attempt to solve that one, because I know it would take an exponentially large amount of time to solve, or forever, or the lifetime of the universe, or more time than we've got, or more time than we're prepared to commit to it. And those are the kind of problems that quantum computers should be able to solve. So we'll talk about more about specific examples later on, but it's not just replacing your computer with a quantum computer. They'll always work hand in hand. So everything we refer to as a quantum algorithm is in fact a hybrid classical quantum algorithm. So it does some of the work on the classical side. When it gets to the point where it says, now search this massive 2 to the n exponential search space, it packages it up, sends it over to a quantum computer, it does a few loops over there, sends the answer back, unpacks it, looks at the answer, decides what to do next. So it's kind of rinse, repeat. So it kind of does a figure of 8 between the classical and the quantum, and it does that until it converges on a solution. You'll gather by now that programming quantum computers is nothing like programming classical computers, which is why I find it so hard, because my brain is completely wired for classical programming, which is why I'm employed as a software engineer. But quantum computing requires this weird sort of sidelong glance at representing problems, manipulating problems, and interpreting the answers. So basically every part of the computation is different in a quantum computer. You know what I mean now. It's because you promised to admit people. Ree's fault, that's why. It works until Zoom interferes. So when's this all going to happen? Well, it's already started, and you can use quantum computers today, and later on I'll tell you how to do it. IBM's mission in life is twofold. One is to bring quantum computing to the world. I don't get a chance to say this very often, but IBM's actually the world leader in this. We're not in most things. We normally do a really good job of following discreetly behind the agile leaders, and respects that because it all works really well. But with quantum computers, we're actually at the forefront of the technology, and that's very exciting and something I'm very proud of. The other thing we do is making the world quantum safe. Now that's a whole other presentation for another day, which I'm not going to give today, but just very quickly, one of the problems with quantum computers, or one of the things about quantum computers, is that one day they'll be able to crack the public key encryption that we use, like RSA and those kind of algorithms that we rely on for almost everything we do. So if you have a secure connection to Amazon to buy something, using it. If you buy something with your credit card, that's using it. Pay by tap, that's using it. If you own a property, the land registry record is signed using RSA. If you DocuSign a document saying this was definitely me, that's RSA. So if someone could crack RSA, all those things. Oh, sorry. It's stand for.
Reverse Shamir, gentlemen.
Yeah.
Thank you. It's the three people who invented public key encryption, which means that you encrypt messages using your private key, and then you publish your public key, which means that so someone could then use the public key to other way around. So somebody encrypts the message using your public key, gives it to you, and only you can decrypt it using your private key, and we totally rely on that for everything that's encrypted. And the name of the algorithm that's most used is RSA. Thank you for telling me what the three guys were.
And it's worth adding also it's rolled out in nearly every company. So the scary part about if it gets broken is then, banks, financial institutions, healthcare companies are all exposed.
Yep.
So at the moment, NIST in the US are currently evaluating which algorithms to use.
Yeah, I was about to say all that. So, thank you, Sarah. Yeah. So if you didn't hear what Sarah just said, so the problem is when that gets cracked, is that all bets will be off. Now the problem is also that there's a thing called harvest now, decrypt later, which means people are stealing encrypted messages right now, squirreling them away on hard disks in the hope that when a cryptographically relevant quantum computer is available, they'll be able to whip them out, decrypt the messages, and find out what you're talking about. Now, that might not be a problem if that's 20 or 30 years' time, which is when we think that's probably going to be, because it requires a really big quantum computer, much bigger than we've got at the moment. But if that's going to be a problem, like maybe the recipe for Coca-Cola, or state secrets, or designs for secret things, there's lots of people who have things which will, in 50 years, 20, 30 years' time, will be really, really embarrassing or financially ruinous if they get decrypted. And that's, so which basically means people have to start moving to the new algorithms right now. And the National Institute for Science and Technology in the US has published the first three, what are referred to as quantum safe algorithms. And all you have to do is start using those instead of the public key algorithms that you use today. Now, problem is, most people haven't got the bandwidth or the people or the skills to go into their existing code bases or their servers and change all these keys for the new ones. So it's a really big journey. Anyone old enough to remember Y2K? Which some people describe as the biggest non-event in IT history. It was only that because some of us, a lot of us, spent the 10 years before adding the extra digits to the date, so it didn't crash the whole world. We now refer to Y2Q, which is this date when you can crack the encrypted messages. And it will be the same thing. You need at least 10 years to transform your organization to be using these new algorithms. Clock's ticking. The World Economic Forum last year, they said probably isn't enough time. The time has already started, that there isn't enough time to move over to that before this becomes a problem. So if you know any CISOs, Chief Information Security Officers in your organizations, tell them they need to start worrying about quantum safe encryption right now. And I'd be happy to talk to them about it in more detail. Yeah, because Zoom's taking the focus. Right. So we have this roadmap for developing quantum technology. You don't need to read the numbers, but the point is that 2029 is a key date. That's when we think that we'll have this, what I refer to as our Gen AI moment. So when ChatGPT came out, the world suddenly changed. Ooh, you can do that now. In somewhere that we think is about 2029-ish, 2 to 3, 4 years from now, then we'll be able to do something useful with a quantum computer that we can't do on a classical computer. So at the moment, no shame in saying that you can't do anything on a quantum computer that you can't do on a fairly big classical computer. But it won't be long before quantum computers are big enough that you can do something useful. And that's the point at which there'll suddenly be business advantage in using a quantum computer. But we're not there yet. And that's the main reason we're going to get there is that, remember I talked about those exponentially large search spaces. If you have a quantum computer with n qubits, which are the quantum computer versions of bits, then the search space you can search is 2 to the power of n. And therefore, every time you add 1 qubit, just 1 qubit, it doubles the power, in inverted commas, of the quantum computer. When I visited IBM's research labs a couple of years ago, they had a 53 qubit quantum computer that they were testing. When that finally got released onto our cloud for people to access, it had 58 qubits. I thought, oh, they managed to squeeze another 5 qubits in. No, that was 32 times more powerful than the one I'd seen. So if I want to double the power of my Mac, I've got to buy 2 Macs. But all I have to do in a quantum computer is add 1 qubit, and it doubles the power of it. So this is pretty cool. It works now. And if you wait till 2029, it'll be too late, because all your competitors who've already started looking at quantum will already know what to do with the quantum computer when it comes. So people have to start now investing in effort in learning about quantum computers, learning how to program, learning the types of problems they're good at solving. Just working on little tiny ones for now, sort of ones which are fairly trivial, knowing that when the time comes, we'll be able to plug in a much bigger problem and solve something which has then business advantage. So people are already using, people are already using about 100 odd qubits in their quantum computer, which has increased rapidly in the last few years. So we think that, we say, if you're not using if you're not using 100 plus qubits, you're not really doing quantum computing, which is a bit disingenuous to those of us who just use a handful of qubits to learn quantum computing. But the point is that if you haven't got a problem that's big enough to stretch 100 plus qubits, then you won't see any quantum advantage. So if your problems are only small ones anyway, you might as well carry on using a classical computer. It's only if you've got these big, hairy problems that would require hundreds of qubits to solve, that's when you're going to see business advantage. So what is quantum computing?
Yes.
You're dying to ask, dying to find out. So quantum computing relies on some techniques or some aspects of quantum physics, which not many people understand, and that's perfectly okay. Richard Feynman, a famous Nobel Prize-winning physicist, said, if you think you understand quantum physics, then you clearly haven't thought about it hard enough. So if he says something like that, then what chance have we got? So we rely on 3 things. One is superposition, and sometimes you hear about this in the press as being, it's 0 and 1 at the same time. Well, it's not really 0 and 1 at the same time. It's actually kind of all states in between. So if you think, actually my t-shirt is a useful visual aid here, coincidentally. So this is how we represent a qubit. And if you think of a point on this sphere, which is called the Bloch sphere, after Herr Bloch, who invented it, as being like a latitude and longitude point, then 0's at the top and 1's at the bottom. You can actually position this lat long point anywhere in between 0 and 1. There's a sort of probability density Schrödinger's wave equations, mapping how probable it is that the dot, the qubit's focus, is in a certain place. And the quantum computer, first of all, puts a qubit into this superposition state, so it's in this kind of floaty state. And then you can send it signals, which are the instructions of a quantum computer, which we call gates, which can move the dot around. So you can move it up, down, left, right. There's actually 3 other dimensions as well, because you've got some phase information as well, but just think of it as moving the dot around on the surface of the sphere, which you use to, so you have a starting point, which is where you are in your current problem state, and then you move it in a way which hopefully pushes you towards a more favorable state, like towards a solution. And then unfortunately, this is a swiney thing about quantum physics, when you look at it to see where the dot is, all the magic evaporates. You've heard of Schrödinger's cat? In one way, it's either dead or alive, or not. Think of it as you don't know whether it's dead or alive until you look at it, and then you open the box, and it is dead or alive. And and before that, it's in this indeterminate state. That's how a qubit is. It's like Schrödinger's cat. But when you look at it, it's either dead or alive, 0 or 1, and it has no choice in between. And if it's in the northern hemisphere, it's probably going to be more likely to be a 0. If it's in the southern hemisphere, it's more likely to be a 1. It's exactly on the equator, it's going to be exactly 50-50. So you've got a beautiful random number generator. And that's often the sort of hello world for quantum computers. You take one qubit, put it into superposition state, rotate the dot round to the equator, then look at it, and it gives you heads or tails. I remember running that. I've still got a tingle down my spine when I think of the first time I ran that program six years ago. I just run that program on a computer that almost nobody else in the world has access to. It's so cool. So that's superposition. Second one is entanglement. This is even weirder. So this is what Einstein called spooky actions at distance, because it really upsets general relativity. What it essentially means, if you entangle two qubits or two objects and then separate them physically, when you look at one, it's a 0, then the other one is automatically also a 0. If that's a 1, it's automatically. It's almost as if when you look at this one, it tells the other one, I was a 0. Oh yeah, I'll become a 0 then. But that appears to happen faster than the speed of light, which general relativity doesn't allow. However, some clever people have bounced photons off satellites and have proved or demonstrated that actually it does appear to happen faster than the speed of light, which is very irritating. So we don't know how it happens. However, we completely rely on it for our quantum computers. So if you entangle a whole load of qubits, n of them, then that's when you can do this whole 2 to the n search space thing for kind of an operation that applies to all of them simultaneously. If this isn't making much sense, that's absolutely fine, by the way. It's really weird stuff. The third one's interference, and that's a little bit simpler. So that's where you apply a simple function to all the qubits, and you encourage the wrong answers to shrink down, the right answers to grow up. So you know, like how you get interference of waves on a pond. You get destructive interference where they cancel each other out, so it's lower. And you get constructive interference where it spikes up higher. So that's what you basically do. So you apply a function which causes the correct answers to peak higher and the wrong answers to drop lower. And you use that to search for your answer. We don't always use that, but that's another technique that's available to us. I won't say you all got that then, because let's say that those are the three principles that we use for quantum computing. So you can see why this is complicated. Now, the good news is most people won't need to worry about this level of stuff in the same way as none of us worry about how a transistor actually works when we use an Excel spreadsheet. We just use an Excel spreadsheet and assume that everything below that has been sorted out by people who know what they're doing. So the same is true of quantum computing. So as we go further, as time goes on, we move further up the value stack, you'll have less and less contact with qubits and gates and superposition and all this nonsense, and you'll just deal with libraries, Python program or whatever language you happen to use, and you just flip the QPU switch and go, oh, I'll use the quantum processor you've got access to then, and it'll do it much quicker. So that's the good news is, but until we get to that point, some people are going to need to program these things. Same as the way we need some machine code programmers in the depths and the bowels of a big computer today, so that other people can run it. It's determined to fight me, isn't it? So we talked about these intractable problems, these problems that we don't allow ourselves to think about. And I think this is actually the most exciting. This bulge on the side, these kind of currently intractable problems, is probably the most exciting area. So I remember I mentioned that there are problems that I don't allow myself to think about because they're too computationally difficult. Imagine when we can start to solve some of those. Well, I can solve a problem like that. Solve this problem over here, which I never thought I could solve before. Ooh, now I can solve this problem over here. And so I think of those as like the unthinkable thoughts. So those of us who are classically trained software engineers, our brains don't allow ourselves to think about those problems. But once we do start to unlock some of those problem areas, that's going to be really exciting area. And it'll just be a cascade of, oh, I can do this now, oh, I can solve that now. one of my colleagues was talking about logistics at a port, how they schedule the cranes and boats coming in to unload all the containers. And the port manager said, well, we can schedule the lorries coming in to pick up the containers, but it'd be really nice if I could also schedule the crews that drive the drivers for the trucks, and then the entry into the distribution warehouses, and then the deliveries to the supermarket. So basically optimize the entire supply chain, not just a bit in my port, because that would make the whole thing so slick. But I can't do that now. It's just computation intractable. I was thinking, maybe one day. That's what we'll use quantum computers for. I'm now thoroughly hating Zoom. Right, so industry use cases. So there are three main areas that we see quantum computing making a contribution. And there are lots of different problems in each of these categories, but think of these three areas. So so one of the big ones is simulating nature. And this is where, again, my friend Richard Feynman said, if you want to simulate nature, then you have to use a quantum physical system to simulate it, because nature is itself quantum, and therefore the simulator also has to be quantum. And he said, comma, damn it, exclamation mark. So that's the only time we've seen the word damn it in a published academic paper. So we use quantum computers, and they're showing great promise here. So there's a huge amount of activity, and we think this is probably going to be the area in which we first see quantum advantage. In fact, I went to a seminar yesterday explaining how this new algorithm will show quantum advantage shortly by our top secret researchers. So things like Daimler-Benz are using quantum computers to simulate the chemistry of electric vehicle batteries to try and find more efficient chemicals to obviously give us longer range on our EVs. Some people are using simulating one part of a paint molecule to look at its reaction to ultraviolet, so they can make paints that are basically last longer and don't fade so quickly. There are people using quantum for new stealth services for fighter aircraft, and the opportunities in sort of computational chemistry, so pharmaceutical drug discovery, where it's all about the steric factors of how one molecule meshes in with another one for the active sites and all that sort of stuff. We can only simulate very small molecules at the moment. I think beryllium hydride, which is the teeniest little molecule you can imagine, is the best we can do. But imagine we can find the true energy state and the exact bond angles of that molecule. But imagine when that's a big multi-hundred atom big pharma molecule, then we'll be designing new drugs with these quantum computers. This end, we've got search and optimization. So most companies are doing some kind of optimization, whether it's DPD trucks around the houses, or whether it's cutting out material from an expensive substance that you want to minimize waste. Lots of people doing some kind of optimization, and that's showing a lot of promise for being amenable to quantum computers, getting a more accurate answer more quickly than you can with a classical computer. Then we've got this middle kind of catch-all bucket in the middle, which is everything else, in which we include things like quantum machine learning, QML, where we use quantum computers to train the models that we then run. This isn't your large language models, this is mathematical, sort of numerical machine learning models. And they're still quite small, so you won't be training Llama or ChatGPT version 10 on a quantum computer anytime soon, but probably famous last words. Oh, actually, probably happen next week. But it's really mathematical models, and they tend to converge quicker. And if it's really high-dimensional problems, they seem to give better answers. I have to admit that the jury's still out a bit on quantum machine learning, because it's one of those. Well, you can do it on a quantum computer. It doesn't seem to be an advantage in doing so. Well, you can do it if you want to, but you might as well just do it on a normal, because it's the same answer, it gives you the same answers. But what we are seeing is that, because quantum computers use true floating point numbers rather than quantized 64-bit IEEE floats, then you've got a slight edge of accuracy down the last digit. And sometimes I think that might give you a slight edge, but it's going to be marginal. But marginal gains is actually something that people are interested in. So if you imagine pharmaceutical drug synthesis, then you can get like 0.01% extra yield out of this big batch of stuff. You end up with a tiny bit of the active ingredient at the end, which then goes into the pills with all the sugar and other stuff. Then that can be worth $100,000 per batch benefit. So it's well worth getting those incremental gains. So that's an area where people can find better answers using quantum. So simulated nature, I'm just going to give you some examples now. So things like lattice models for molecules, electronic structure for working out the bond energy, the bond angles, and the energy wells, so the energy in which a molecule is stable, and also for vibrational things, so in steady state, what does the molecule look like? Things like machine learning, regression, scenarios. So simulation, people often ask me, can we use it for sort of wargaming or simulation? Maybe. So I think there's an application of quantum in digital twins, so actually running the real world model that you put in the twin of the physical system. So you perhaps simulate nature better using a quantum computer. Maybe, don't know yet, but early days for that. And then there's the different aspects of Monte Carlo methods and optimization, combinatorial optimization that he's something fun with my computer, in the optimization box. And it tends to be that different companies have several of these. So they don't just have one problem in the simulating nature category. They normally have like an optimization, and so you can look around and say, oh, well, that one and that one and that one are amenable to quantum. So let's look at those first. And we're seeing it in all sorts of different applications in different industries. And you can pick your favorite industry here and pick application. These aren't just things we made up. These are things that our clients are actually working on in these areas. So we've got hundreds of companies who are members of our quantum network, and they're all working on various things. And the thing is that no one's really found the killer application for quantum yet. And this SQD quantum chemical algorithm that I was talking about yesterday is a real candidate for possibly showing quantum advantage. But everyone's trying to find the thing which will make a difference, give them business advantage in their particular industry. And this is why you have to get started now, not wait till it comes, because people are doing this today, so that when the time does come, they will switch over to using quantum computers to solve these big gnarly problems and gain competitive advantage. And if you're not in that company, then you'll lose out to them. But same as the way, like, the first person who did high volume trading, it's like they made $1 trillion the first day. Everyone went, $1 trillion. So of course then everybody else did it the next day, and then everybody else is making $1 trillion, so then it all kind of leveled back down again. Traders in the room, sorry, simply oversimplified this, but same will become true of quantum, that there'll be huge competitive advantage to the person who cracks one of these problems first, and then gets access to one of our big quantum computers to run it on. These are some examples of some actual real named customers who are doing stuff. So ExxonMobil's doing some stuff optimizing the energy use of their tankers transporting the oil to try and reduce the amount of oil they use to move the oil. Moderna is, although we're way off being able to simulate actual molecules, they're looking at how they would use it to do mRNA therapeutics. They're starting to look at that because they see it's being really big. In the financial services sector, you get things like portfolio optimization, risk assessment, portfolio balancing, and settlement between banks, being looked at by various other banks. And HSBC is looking at fraud detection, so very small signals in large amounts of data. Not sure it's going to work for that, but we'll let them try. It might do. We might get something out of it. The problem is that quantum computers aren't very good for big data because of this thing where as soon as you look at the qubit, the magic smoke comes out and it turns into a bit. So you can't feed additional data into a qubit once you've started playing with it. That's tantamount. You have to do read, update, then write. So what we normally say is you get rid of 99% of your data using traditional classical methods, then you'll look for the sharpest needle in the remaining 1% of the haystack using your quantum algorithm. That's probably how we see that. Now we've talked about quantum advantage. you'll tell me, is the point where we can do something useful with a quantum computer, which we think is 2 to 3, 4 years away. But in the meantime, we've coined this term quantum utility, which is kind of a flag of convenience. It's just like a not quite quantum advantage, so it's the utility in the sense of useful. And we've already passed that point. So in 2023, we demonstrated that we've now run off the end of the biggest quantum computer we've got. You can't quite simulate it on a classical computer. So you can't quite run the simulator for the quantum computer, which is part of our software, the Qiskit software, on a normal classical computer and get the same results as you do on the quantum computer. So we've kind of gone off the end of being able to just say, oh, we're running on the laptop, and that'll be the same as we get on the quantum computer. Now, this gives us a problem, because how do we now verify that the quantum computer was right? You can't run it, you can't get the same accuracy on the classical computer unless you run it for a really, really long period of time. So we've got this real challenge of verifiability, of how you, as quantum computers get bigger, how we trust their answers. Now, I have to say, that shouldn't be too much of a shock, because if you build an Excel spreadsheet with 100,000 numbers in it, you don't go around all of them to check the formula was actually right. You trust that if you do copy, paste, drag, paste, they're all the same, they're all right. Okay, some people just check the corners and the middle one just to make sure, but in general, you don't bother because you trust the computer to be right. But you don't allow for the fact that a cosmic ray might have come in and changed one bit of a thing. We do it with memory already. The fact that you have a parity based on a memory chip. If you do get a cosmic ray which flips a bit, then you get a parity error. You have to go back and check it, and go and correct it. So quantum utility, we have passed that point. So we're in this kind of netherland now before we hit quantum advantage, which is all very exciting. So the next 4 years are going to be quite exciting times for quantum computing, and we're moving towards error mitigation and error correction. The problem with quantum computers today is that what's called NISQ, noisy intermediate scale quantum, which means the qubits that we have are quite noisy, mainly because they're very, very, very cold, down at very close to absolute zero, 15 millikelvin, which is ridiculously cold. Just by comparison, the Hawking radiation, background radiation temperature of the universe is about 4 Kelvin. That's balmy by comparison with 15 millikelvin. That's really hot. So you don't want to put your tongue on one of these things, tell you, it'll stick. And we control them, those little pulses I talked about for manipulating the qubit, are sent with tiny little microwave pulses. Now, of course, if you fire microwave pulses at something, as we know, when we cook our dinner, it gets hot. So eventually, we're talking about 100 microseconds after you start, the whole thing decoheres into thermal noise, and you just get a very expensive random number generator. So you have to get all your computation done in 100 microseconds before it boils over, but turns to mush, and you have to reboot it. So nonetheless, if your instructions are very short, you can actually get a reasonable amount of computing done in that time. So in order to get away from that, we move towards what we call error correction. Now, the algorithm I talked about way back at the beginning to crack encrypted public key encryption is called Shor's algorithm, which requires thousands of perfect logical qubits, so mathematically pure ones that behave with the matrix multiplications that mathematical qubits do. We're way off that yet, and for quite a few years there's been this big debate about how many noisy qubits does it make to make one logical qubit. Some people said 1 million, some people said 10,000. Now we think it's 144, so we kind of go with it's called the gross code. It uses a gross of noisy qubits to make one logical qubit. So in order to get, we need lots and lots and lots and lots of qubits in order to run Shor's algorithm to crack even the keys that we use today. And if we keep extending the keys, then that'll be even harder. But nonetheless, that algorithm does crack public key encryption because it can factorize numbers, and public key encryption relies on you multiplying two numbers together, which is easy to do, but you can't factorize the number. The reverse operation is almost impossible.
Excuse me, when you say Shor, how's that spelled?
S-H-O-R.
S-H-O-R.
Peter Shor, who's alive and well and works in MIT or Stanford, one or two, but yes, he did it in 1991.
He's American.
Sorry?
Is he American or British?
Yes. Yep. Now, whether he's actually American or whether he lives in America, I wouldn't like to say. I've got a feeling he might be English, but definitely stuff in there. So people are already doing experiments now, which are in this utility era. So remember I said the 100 qubits thing. So we put down this 100 by 100 challenge. So if you can occupy 100 qubits doing 100 instructions, we'll give you a quantum computer that can do that. If you can fill that space with quantum gates, you're probably doing a problem which is close to quantum advantage. And, the gauntlet's down, and lots of people are trying to do that at Los Alamos and various universities around the world. I won't go into what they're actually doing, or some of these chemical simulations. So, as I mentioned, we've got lots of people using our quantum computers. We've got the biggest fleets that are collected now for quantum computers. We've got more than 10 online in our quantum data center in Poughkeepsie, upstate New York, and 3 in our European data center in Einigen in Germany, and several others in actual client locations. So we made our quantum systems available in the cloud in 2016, long before anybody else even thought of it. And most of our customers they don't have their own quantum computer. They access ours via an API in the cloud. So you have this programming language called Qiskit, Qiskit, which is a library that goes into Python. You write your quantum program in there. You do the classical part of your computation in the Python that surrounds it. Use that to load up the values into the quantum program. Then you either send it to the simulator, which is running your laptop, or you send it off through the same API but with a different flag to a real quantum computer in the cloud. You normally run it a few times. Remember I said that when you look at the bit, it turns into 0 or 1. The way to find out whether it was closer to the top or closer to the bottom is to run it about 1,000 times and count how many times you get each answer back. You can build a sort of probability distribution, a bit like a mass spectrometer reading, and then figure out from that what it was trying to tell you. So reverse engineering the answer from those ones and zeros is quite clever and quite difficult, but that's what we do to do it. So you get that answer back, you unpack the answer, decide what to do next, and you keep going around in a loop. You hopefully get converged to an answer. We have various plans for people to access the quantum computer. Some of them are free, you get access to the big quantum computers, but you only get a limited number of seconds of runtime in a month. And then it's a bit like phone plans, so you can do pay-as-you-go, or you can do a flex plan where you have so many minutes per month, or you can have more and more. And over on this side, you actually get a slice of a quantum computer, like an eighth or a quarter, which is dedicated to you. So you can use it any time of the day or night you want. It's there waiting for you, sitting there, humming away, 15 millikelvin, waiting for you to chuck jobs at it. And depending on what your level of use is, same with phones, different ones will make academic, financial sense to different people. But the good news is you can play with them for free, mainly because we need people to be able to program quantum computers, because as I've alluded to, it's quite difficult, and if no one can program these things, we're going to be a bit stuck, because we'll have produced these quantum computers, but no one will know what to do with them. So what we want is to train a whole generation of quantum software engineers who think this weird way, and they know how to program Qiskit, and they've got their Qiskit developer badge and the certification to show that they can program quantum computers, have that on their CV, ready to go to the marketplace. And one of my banking clients told me a couple of months ago that he actually hired his first quantum software engineer, and I said, "Oh, that's good." He says, "Oh, apparently he used to work for you." Sure, he's excellent in that case. It's already starting. So this slide's really funny. It used to fit on one slide, and then the font got smaller and smaller and smaller until you couldn't read the font. So then somebody had the bright idea of making it scroll. So these are all the people who are members of our quantum network, and there's academic institutions, banking institutions, chemical companies, all sorts of folks. You might recognize some names in there. More than 250 people now, and that number keeps going up every week. People are realizing that the race to start understanding quantum and getting the skills is really on, and they need that quantum advantage thing when it comes. We do also offer a consulting engagement, so if you want some help doing this, as well as learning it yourself, we can actually look around your organization and sort of do a heat map of, say, so these algorithms over here might be useful for quantum, these ones over here might be, and let's pick this one to start, and we'll get you going. We'll kind of do a 9-month engagement to 9 months to a year to look at the first problem and build a prototype of it and get it going, and we'll work with your people to train them up so when we leave, you'll know what you're doing with quantum and you'll have an actual working use case, which hopefully will be your first quantum advantage algorithm when the time comes. That's available now. And because of this combination of classical and quantum systems working together, we talk about a quantum-centric supercomputer. So you can imagine high-performance computing resources in the future having lots of CPUs, lots of GPUs, because obviously you'll need that for the AI bit, and lots of QPUs, quantum processing units, all kind of co-located, so you can farm the correct bit of the algorithm over to the right place at the right time, and that thing collectively solves your problems for you. And that's pretty exciting. We're talking to various people now about trying to build these things. They want to co-locate IBM quantum system with a whole bunch of high-performance compute, so they can actually solve some meaty problems. Now, I'm just going to talk about hardware again for a minute, not in a scary quantum physics sort of way this time. So we've actually designed, so all of our quantum computing chips are named after birds. The Condor chip had 1,000 qubits on it. Massive chip. I've got a picture of it somewhere. There it is, massive chip, huge thing. We squeezed just over 1,000 qubits onto it, but not very good. They're really noisy and you get a lot of crosstalk and they can interfere with each other. It's like really terrible. But we learned so much building that chip, you can get it vaguely work, that we built the Heron. Only has 133 qubits, or 156 in its version 2. And what we've decided, and the beauty of these is because they benefited from our research and development work on the Condor chip, they have almost zero noise. They're almost perfect chips. They're not perfect qubits, but they're really, really good. So what we decided to do is build quantum computers out of these 156 qubit modules. So you know how you build, you may or may not know, if you build distributed computers today, you just take several computers and you join them together with communication links and spread the computation across them. We can now take this Heron chip, 156 qubits, and join them together with these couplers, which are just under 1 meter long, and they maintain the entanglement across just under a meter. So you can entangle 2 Heron chips together and have the whole lot entangled together. Unfortunately, we can only do about 1 meter long, which means it can only go like within one of these things, like Marie's earring here, these cryostats that we have inside our quantum computers. You only go within the cryostat. But one day, and we hope it's quite soon, we're going to extend these cables and have these entangled links. They'll probably be using photonics or some other technology, because these are just using a cable, to be able to link several quantum computers together, so we'll be able to build distributed systems. So then you just kind of either build them out that way or build them upwards, so you can stack them however you want. So then that's how our roadmap, if you're looking at the numbers on the right hand side, we're talking about tens of thousands of qubits. You can say, well, you just build more quantum computers, and we make them hexagonal. So we've kind of appealed to beehives, because hexagons tessellate better than the other shape. So when you park them together, that minimises the distance between them, so that'll minimise the length of the entangled links we're going to need. So we thought about this, but we haven't actually got those long links yet. But when the time comes, we'll be able to stick them all together. I talked about Qiskit. This is the Python programming language. You can either download it. It's all open source. You just apt-get install pip install Qiskit on Python. Or you can go into IBM's cloud and play with it in a Jupyter notebook in the cloud and use ours. Up to you. And you can either use the simulator or you can use the real quantum computer. The good thing about Qiskit is that most other quantum computer manufacturers, and as I mentioned, we're leading the pack, but there are other, we do have competitors much smaller than us, and they've all chosen Qiskit as well. because we don't want the ridiculous proliferation of programming languages that we have with classical, where if you don't like one feature of your programming language, you invent another programming language just for the sake of it. You know, I'm not pointing any fingers, but you know who I mean. But so you know, quantum programming is hard enough as it is, so let's just have one language for doing it and just use Qiskit. Now, Microsoft disagrees with that. They've invented Q#, so they would. They haven't got a quantum computer yet, but they've got a language to do it. I'm sure they'll get it eventually. So if there's any Microsoft in the room. I said that in front of a Microsoft person today, and they said, yeah, absolutely right. So there's no harm in learning Qiskit, even if you don't use IBM's quantum computers, which I'm sure you will, because we're the only person who actually offers a commercial service, but it's worth having that on your CV. So as I mentioned, we need to train people to use quantum computers, so we've got lots of online courses that anyone can access. We help universities teach modules using hands-on labs, using the IBM stuff, giving access to our cloud. And you can get certification in Qiskit programming. I'm a Qiskit developer. It's quite a hard exam, actually, mainly because it was a timed exam. I haven't sat a timed exam for over 40 years. What's this clock doing in the corner? Oh my God, it's counting down. Okay. So if you want to play the quantum computer, you go to quantum.ibm.com, get an ID, which is free, and then you can log in and you can play with one of our quantum computers, either using a Jupyter notebook, or there's this really cool graphical designer, which is a bit like Node-RED for quantum, where you can kind of just drag gates onto a music stave notation, because you get 5 qubits to start with, so it looks like a music stave. You drag the gates onto it. There's just different ways of playing around with it to start with, but Qiskit is a very serious language. That's what all these high-powered research institutes are using to program their algorithms. And so the main thing is there's lots of learning material there, starting with the Hello World, the quantum coin flip that I talked about earlier. Qiskit Summer School, which thousands of people attend, which is all on YouTube afterwards, so you can go back and watch those. Certification. And McKinsey reckons that 33% of the quantum job opportunities are currently unfilled, because people haven't got the skills yet. So if you know any software engineers, tell them to learn Qiskit, give them their CV. So going back, we have this dual goal now of getting bigger and faster quantum computers and finding some interesting gnarly problems to run on it. And in the middle will be this quantum advantage, actually finding something useful to the quantum computer. So just have a think about what problems have you got in your organisation that you're not exploring now because they're too computationally difficult for classical methods. That may well be the in for quantum computing.
So I'm going to just stand here because I think we've got a bit of time for questions. We've got people online, so Christian and Marie, let me know if anyone online also asks a question. But if there are any questions in the room, now is your opportunity.
Hi.
Hi.
What are IBM or governments and leaders in quantum computing doing to make sure that the legal framework is not falling behind technological advancement, so we don't end up with a quantum dark web, or it's being used for more nefarious reasons by governments? If you talked about your
Cracking encryption keys, for example.
you talked about the port and it being slick, that could be used for military purposes.
Mm-hmm. Absolutely.
And sorry, another question. We all know about AI and its demand on energy and the environmental impact. Can you talk us through quantum computing?
Great question. Okay, right. So the first question, yes, so quantum ethics is very much a thing. We work at the BCS with, because the legal framework and the governance around it needs to grow up, not so much to regulate it, it's just a computer, right? But so that the legal profession understands what's coming, so that when someone does do something nefarious, they'll have the right words in their vocabulary to be able to prosecute and defend and judge and all those kind of things. So and to write contracts which include the right words for the quantum stuff that's coming. So
are governments thinking about it already?
Yep. Second question, much more interesting to me. So I mentioned these things run at 15 millikelvin, so they have a refrigerator. Look at Marie's earring. So the top of that refrigerator is about 40 Kelvin, so it's still pretty damn cold, and 15 millikelvin at the bottom. It takes about 10 to 20 kilowatts of power to run that refrigerator. That's it. Because the rest of the thing is these teensy-weensy little microwave pulses, which you want to be as small as possible, otherwise they'll make things warm up too quickly. So the delta on the power is really just the refrigerator. And you can get lots of qubits. You can keep adding qubits. Remember I said that every time you add one qubit, it doubles in power. You can just add loads more qubits into one refrigerator. So the power goes sort of, let's call it 10K for the sake of argument, 10K, 10K, and then you go, oh, fill that one up, okay, 20K, 20K. Now 20K is nothing compared to the data center. I mean, absolutely, they use tens of megawatts, you know, loads and loads. So it's really, really small. And it only scales, the power consumption scales linearly, whereas the power of the quantum computer scales exponentially. So it's a really good story from a power consumption point of view. However, there's always a but. Remember I talked about the classical computers that go with the quantum computers to do the hybrid classical quantum algorithms. They use the same amount of power as normal computers use. So if you need a whole load of classical computers to keep your quantum computer fed with problems, then that's going to have a fairly hefty power bill, but no worse than the current situation.
Today, CPU read electric beats almost error-free. And you mentioned that the QPUs always had challenge in reading the qubits. Could you give a number of the state-of-art QPUs error rates in doing this job?
I don't know that number. So if you Google IBM quantum computer error rates, it will actually, it's on this slide. I don't think we can zoom in enough to see it. It's on that slide there. It tells. Okay, so if you log into the quantum computer, it tells you all the quantum systems are, oh, not that one. It said you can log in. Wherever it is. If you log into the quantum computer system, it tells you all the quantum systems are online, and you can click on it. It tells you all the error rates and the when it was last rebooted and all the tuning parameters. Because what you can do is we characterize each quantum computer, and we get the noise matrix for each of our quantum chips, which you can then download into Qiskit on your laptop. So you can then emulate an actual quantum computer with the exact noise parameters on your laptop, so it will behave exactly like the quantum computer you can finally run it on. I can't find that at the moment, so I can't answer that question, sorry. But information is available. Yes.
You talked about the hyperbole in the media, and that's probably most about a lot of people's introduction to quantum computing. Are you able to put into context things which have been recently said to be, you know, groundbreaking, like NVIDIA's super quantum computer the other day and Microsoft's Majorana one chip? Like, how is that?
So NVIDIA argue they haven't got a quantum computer at all, but they say you don't need a quantum computer, you just simulate it and run it on GPUs. Obviously they would, wouldn't they, because they make GPUs. Of course, they use tons of power in order to simulate a quantum computer. And as I mentioned, we've now entered this quantum utility era where we've got quantum computers that are big enough that you can't reasonably simulate on classical computers. So to a point you can simulate them using GPUs, you have to use a real quantum computer, and we're now in that era.